what kind of questions can we ask ourselves in the physics world? That's my topic today. Well, you probably have heard about many things like what is dark matter, do we have extra dimensions, or what is string theory and does it play a role in our daily life? So today I'm going to try to give you a little glimpse into those main topics. It's quite ambitious because there are 5 things, so please pay attention. So first of all would be to understand a little bit matter, what can we find? What is dark matter? What about extra dimensions? You know much more than what you expect about antimatter, and how can we study the evolution of the universe? So first of all, one way to do, it's not the only way, you know, there are a large number of methods. You can collide particles to study matter. So this is a very nice collision that you get in one experiment happening at CERN called ATLAS. We recorded that. You can see the date, times, the number of events, and so on. And what happens is that you have particles colliding, coming from both sides, and they collide to the center. We are very good to control those things and so on. And then you have many tracks. You see this orange stuff and so on, millions, billions of tracks. Well, one first thing you use to study those things is that, of course, you have to respect Einstein's rule, the famous E = mc squared stuff, and then you can go on and study matter. So today, your understanding is probably up to that. So you know matter is composed of molecules, and also molecules are composed by atoms. So that's what you see around, and then inside one atom you have a nucleus with protons and neutrons, and electrons flying around. Then we know further, for something like 40 years, that we have quarks inside those protons and neutrons. Okay, so these are the smallest ones. We call them elementary particles. And that's where we stand now with electrons and quarks. But after a century of measurements and so on, we have found a lot of particles. And for instance, we have built something called the standard model. So there are more than hundreds of those. You know the electron and proton, but there are some other strange names that we can build on this, like muon tau, quark top, muon neutrino, and so on, many. K short, lambda star. We are crazy with Greek letters, you know. And then on these 2 things, you see the 2 first rows or so. No, the 3 times 2, okay, 6 plus 6 rows, you have the components of matter, okay? All the guys with glasses and so on. This is building all matter we can know, all matter we can measure, at the same time, the one we have right now, the one we have in the future, the ones we have in the past, anytime, okay? And you are made, in short, you are made of the same things than the ground, the trees, and a piece of gas in the galaxy. Maybe you don't like it, but that's reality now. And to organize this full world, you have 4 main interactions, forces. You know a little bit about electromagnetism, for instance, the little guy here. And when you put a magnet on a fridge, you know. And there are some others called strong interaction here, weak interaction, and gravity. Okay, gravity, we know it's there, but particles are very, very light, so they are not very sensitive to it. But strong interaction is very important because, for instance, they keep the proton and neutron stable. And remember, I told you, we are all made of protons and neutrons. So this guy, this one, is preventing you from vanishing into nature immediately, okay? So thanks to him. And after many observations and so on, we don't understand fully this model because if you extend those things at higher energies, very, very higher energies, some things are wrong, that you got some probabilities crazy beyond 1 and so on. So we have tried to find something called the Higgs particle, like a missing puzzle, a missing part in a puzzle. And how does it work? You have a particle generating a field, so this is a kind, okay, you have explanations, but maybe don't read those things, it's too complicated. And you have the field, and when particles could go through, they would interact, they would feel it, like, you know, you walk in a swamp and then you are stopped because you have many things, trees and trees and trees and more and so on. And then you have things called like strong interactions that could result in more massive particles. Okay, so in short, you have the slower you get, the heaviest you are, and the faster you get, the lightest you are. And that's what we try to find now. So, how to summarize our searches today? Here. Okay, it's not so really obvious, but that's what the kind of thing we can publish in papers, actually, you know. And maybe if something gets to this year, we will publish in Nature, Science, and really relevant sources. So, to explain it to you in, 20 seconds? You have the red line, okay, corresponding to 1. What is below? Okay, it's a function of probability as a function of the energy of the particle we would like to find. So we don't know where it is, you know. We try to test, and after some measurements, we are excluding, testing, and so on, some region. So what is below the red line is we have excluded any possibilities that the Higgs exists there. You see, we have a lot of black points. These are data, a lot below, okay? And above possible existence, this means that maybe we could still find the Higgs, like maybe in this region here, you see. And what is really exciting nowadays at CERN and the physics lab in Geneva, that most of you might know, is that this year we will collect enough data to see if this bump is still there or if it disappears, okay? So stay tuned, because after summer we would say like, okay, we have found the Higgs, and then so on, and then so on, and then you're gonna die, or you're gonna fly, or you're gonna disappear, or whatever. So that's one main topic, but let's come to something even more strange. All the stuff, the guys, the piece of matter, the Higgs boson and so on, this is only 4% of the whole universe, all kind of matter and energy. You see? This is the red part. Oh, okay, sorry. No, I want to stay there, just a second. And if you study the rotations of galaxies and so on, you can't explain everything because we know gravitation and so on, you know the rules, you can calculate those things. I don't do it myself, I let this to theorists and crazy guys, even more crazy than me, I feel. And you can calculate that we need something about 23% of dark matter. In short, we don't know what it is. We call it dark because we don't see it. We call it matter because we feel it should work as matter, that's all. Another thing, other observations, which I don't know at all about, says that we could have also something called dark energy, even stranger, okay? And so to study those things, we are looking everywhere, you know? And for instance, it can be hidden or related to something called extra dimension. So, you know, we live in a 4-dimension space and time, but maybe we are preferring 11 dimensions. It's not 7, 8, or 20, it's 11. I don't know why, but okay. You know, they are theorists and they know better than us. And this is how we could have represented, actually, extra dimensions. Now let's come to a very different topic that I told you, you know a lot about this. This is antimatter. First of all, because I would forget if I don't tell it right now, what is the definition? Okay, definition simply is the opposite electric charge. So if you have a piece of something which is charged, negatively charged, the opposite or antimatter is positively charged, okay? Electron E minus, a positron, the first guy, is E plus, and that's all. And so when you collide particles, you have a lot. We produced a lot. At CERN, we produced in 95 a lot of antiprotons. But okay, in some movies, like maybe you have seen Angels and Demons with Tom Hanks and so on, they put it in this kind of very nice box, okay? We would love to have that, physicists, because we don't know how to do this so far, okay? And they steal it from CERN to bring it to the Vatican. So if you go to the Vatican, please take a bit of it to us back. And in reality, you know, you need a lot of accelerators. We call that decelerators with a lot of facilities, as you can see there. This is at CERN. And we are actually storing antimatter, antiprotons, anti-hydrogen, and it's quite hard to build. And we maintain them for 15 minutes during the last year, for instance. So you see, this is the reality about that. So we have a lot of understanding, and even some medical applications around proton therapy, anti-proton therapy, and so on. Okay, so a little bit about other experiments trying to understand those questions again in a different way, like in space. You probably have heard about the International Space Station, you know, it's very, very nice and so on. We are sending some detectors on the station, like this one called AMS, you see. And by studying the universe, it can also actually understand a little bit better what is dark matter, or at least try to find it, because we don't know where it is, and continue to measure antimatter, because we know quite well, okay? One key thing about antimatter, you know, is that at the earliest days of the universe, we had the same amount of matter and antimatter. And today, hopefully, we are just made of matter around, because if you would have antimatter, you know, we would also disappear by colliding and so on. So something happened, and we can't explain this so far. So at the same time, they also study the evolution of the universe, I said. So a few key things, you know, a few key things we know. It's 13.7 billion years old. It's quite precise, you see. They say 15 million, billion, we didn't know in the past. And we started from a very small box, so don't ask us what is a Big Bang. We don't know because everything happened afterwards. The goal or the idea is to get as close as possible, but we can get as close to about 1 picosecond, you know? You know, maybe most of you don't know 1 picosecond, so let me explain. 1 millisecond, 1 microsecond, 1 nanosecond, 1 picosecond. See that? Very fast. And so at some point, something happened. You had everything, any piece of energy and matter within a very small sphere. It was very, very hot, more than the temperature inside of the sun. And then everything expanded. And at some point, you had an emission of, after 300,000 years, an emission of a lot of rays and energy. I will show that just afterwards. And then you produced matter, galaxies, clouds of gas, and so on. We somehow exclude a little bit thinking, religion, blah, 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 okay? Just to be safe. And at some point, you produced all the matter we know today. There are some experiments like WMAP, trying to measure this. Some other more a bit sexy called Pamela, okay, are also doing this. And then finally, you can get this beautiful picture, okay? This is the whole universe, you know, okay? So don't ask us again, what is beyond? What is this black stuff? We don't know, okay? We know it's expanding, accelerated, and so on, but we don't know more than that. And what is interesting there is that you see different colors. You see these red points and these blue points. This is showing you a difference in terms of density. In some region, you have more energy. And this is a picture from the past, you see, because this thing is measured at the very outer region of space. So somehow we can get very far in space, but also very far back in time, okay? And this is very interesting for us. So I hope I showed you a little bit about how we can really question ourselves in our physics world, really every day, you know, because we are working on this. This year would be very exciting for CERN, so we would progress a little bit on all these topics. And just to conclude, I wanted maybe to let you know a little bit about my experience there, because I work as a physicist since 2005. This is really a fascinating world, actually, because every day is different. You see, you can learn about those things in a very simple way. Just read and listen to nice people. And we also share a lot of knowledge. We can meet very interesting people, not only good in physics and science, but also in literature, in philosophy, in music, and so on. And yeah, I really hope to continue there. And I was really happy to share a little bit of this with you today. Thank you.
Merci Marc, vous m'avez offert ce doux tournis qui était le mien au sortir des cours de maths. Pour replacer un peu dans le contexte, j'avais 1 de moyenne, la présence. Finalement, vous n'êtes pas mal, question vulgarisation. Pour comprendre pourquoi je dis ça, je me permets juste de lire le titre de votre thèse. La simulation...
Je ne m'en souviens pas exactement.
Alors, moi non plus. La simulation et détermination des quantités de matière du trajectomètre à rayonnement de transition de l'expérience Atlas, étalonnage et alignement du détecteur avec des données cosmiques et estimation des sections efficaces de production des désintégrations WEV et ZEE au LHC.
Ok, merci. Merci beaucoup.